Hello and welcome back. So in the last video we talked about the size of general unions, and now we would like to decide Cartesian products. So if you have a set, for example AB, and another set 1, 2, 3, the set AB is size 2, the set 1, 2, 3 is size 3, the size of the Cartesian product AB times 1, 2, 3 is the size, as we know, of this set here, A1, A2, A3, B1, B2, B3. As we know, this is the Cartesian product of these two sets. And the size of this set, well, we have 3 elements in the first row, and so it's 3 elements in the first row and 3 elements in the second row. And these elements are disjoint. The elements here are different from the elements here. So therefore, by the addition rule, the number of elements is 3 plus 3, which is the same as 2 times 3, which is 6. Okay. And here's another interpretation of the same result. We have here all the elements, A1, A2, and 3, B1, B2, B3. We have 2 rows and 3 columns, so the total number of elements that we have is 2 times 3, which is 6. It's essentially the same argument, but maybe this gives more of an idea of a volume or an area. All right, so like this, the area is 2 times 3, which is 6. Now, in general, we can see that the size of a Cartesian product is the product of the set sizes. So if you have 2 sets A and B, then the size of the Cartesian product A times B is just going to be the size of A times the size of B. Okay, and this is called the product rule, which we'll denote by this X. And as you can see, it's another application of the addition rule because we just add things, the size of A times. So here we added them twice. So it's just like a generalization, if you want, of the addition rule. Okay, here are some applications of Cartesian products. Let's start with the ubiquitous tables. So every table, as we had said, that we use is a Cartesian product. It has records which are viewed as rows. Here we have 5 records, and it has attributes here which are viewed as columns. Here we have 3, and the number of cells that we have is the size of this Cartesian product, number of views, and by the multiplication principle is going to, or the product rule, it's going to be 5 times 3, which is 15 cells. All right. If you have more than 2 sets, so A times B, the Cartesian product, is a set of all A, B such that A is in A and B is in B, and this gives you a rectangle like that. And the size of the rectangle, as we saw, is just the product of the sizes of the 2 sets. If we have a Cartesian product of 3 sets, it's the collection of all A, B, C, such that A is in A, B is in B, and C is in C. And that will, instead of a rectangle, is going to give us like a cuboid, something that looks like that. And the number of elements there is going to be the size of this Cartesian product. It's the number of elements. It's the size of A times the size of B times the size of C. Okay, so let's see an example. We have someone who likes to dress differently, and they have 3 shirts, let's say, 2 pants, and 5 pairs of shoes, and one wonders how many days they can go with different outfits. So how many different outfits can they have? So notice that an outfit is just a triple. It's a shirt, a pant, a pair of pants, and a pair of shoes. So for example, an outfit might be the yellow shirt, the blue pants, and the red shoes. Okay, so the outfit is just an ordered triple. And the set of outfits, so there's an outfit, and the set of outfits is the set of 3 tuples or ordered triples, which is just the Cartesian product of all shirts times all pants times all shoes. It's a Cartesian product. And the size of the number of outfits, namely the number of different outfits that there are, is by the product rule, is going to be the number of shirts times the number of pants times the number of shoes. And in this case, it's going to be 3 times 2 times 5, 3 times 2 times 5, which is 30. Okay. And you might think, oh, this is again not very useful, just counting number of outfits. Maybe the following example will convince you that this is indispensable. So let's say you go to Costco and you want to buy tissue paper, okay, bathroom tissue. And so you get a package that looks a little bit like that, and trying to count how many roles there are is hopeless. But what you can do is you can count and see that there are maybe the sizes are 3 by 3 by 4, and therefore by the product rule, the number of roles that you have is 3 times 3 times 4, which is 36. All right. So if you have n sets, then again you can use the product rule in induction. You get the size of A1, Cartesian product A2 up to AN is just the product of the sizes. And here's an application of that. Suppose you want to go for lunch, you want to go Subway, and ask how many sandwiches can Subway make. And let's say that they have 2 breads, wheat and Italian. They have, let's say, 5 meats listed here, 3 cheeses, 4 veggies, 3 sauces. And let's say that you need to create a sandwich, you need to choose one of each. So you need to choose a bread and a meat and a cheese and so on. Then the set of all sandwiches that you can make is the Cartesian product of all breads times all meats times the set of cheeses and so on, because every sandwich consists of just one element from each. Okay, and you can choose all those breads and so on. Okay, so the number of sandwiches is going to be the product of the number of breads and so on. Okay, and that's going to be by the product rule, and that's going to be equal to 2 times 5 times 3 times 4 times 3, which is 360. Now, in fact, they have many more choices, and the number of sandwiches they can make is actually quite astronomical. All right, so to summarize, we talked about the product rule that says that the size of A Cartesian product with B is the size of A times the size of B. We denoted it by this multiplication sign. We said that for multiple sets, the size of the Cartesian product is again the product of the sizes. And what are we going to talk about next time? Cartesian powers. See you then.